konferans yapıyoruz şimdi. Okay, today our guest is Tzur. He's a professor at University of Colorado, Denver. Do you know where Denver is? Colorado?
I know.
You know? Okay, good. Yeah. He has a very interesting life. Born and raised in Kibbutz, Israel. We talked about it this morning. He did his PhD at University of Georgia, where I did, actually. So he was, I used to read his journal papers for my dissertation too. His work is also about fractions, children's understanding of fractions, and teacher education, and how to train teachers to have second-order models of children's thinking. So we are very happy to have him here. He has so much research. He has like 30 pages of CV, resume. You can check online. Very long resume. We are very glad to have him. He used to be at China this year, past year, I guess, and he has some research all over the world. So we are collaborating with him. Gülseren also from Boğaziçi, Bosphorus University, she's here. And our students. So I'm leaving the stage for you. Thank you for coming again. And he will be here with us today and maybe this afternoon too. So we're going to talk about some research too. So if you're interested, maybe we will see. And if you're interested in future studies in US, like similar topics, he's a good person too. He has some money for research.
I don't. The university has.
Good. Okay, thank you.
Thank you very much. Thank you, Zelas. Thank you, Gülseren, for allowing me to come to Turkey and do some work together and also share with you some of the stuff we've been doing. As Ella said, it will take 2 days for me to share with you a little bit of what I've been engaged in, and that would just be the start. But what we decided to do today is talk a little bit about students' numerical reasoning and how it relates to teaching. 2 days ago, we had a seminar about teaching and about teacher thinking, how they think about learning and how that impacts what they do. Today, I'm going to look at the other side and try to link the teaching and the learning. It's possible for anyone to say, oh, numbers, that's elementary. We at least work, and I saw it in China, and I think it's all around the world, a lot of people whose numerical reasoning at 7th grade, 9th grade, 12th grade, even at the university. And I'll point out to something that you would say, ooh, maybe me too. So this is not just about elementary kids, though. If we do the work at the elementary, we are likely not to see it again as a problem later on. So that's basically where I'm coming from. The thanks I'm owing to all my team. The EdPed stands for Student Adaptive Pedagogy. It's an idea of teaching that is not based on curriculum, that is not suggesting the kids need to learn because we in Ankara or in Washington or in Denver told you, the teacher, what to do, but rather you know as a professional what needs to happen with the kids. The project is funded by the National Science Foundation in the United States. We've been working for nearly 3 years now, and you will see some of that stuff. So I feel obligated and honored to work with these people and to represent some of the stuff we were doing. And thank you all for coming. I appreciate you taking the time out of whatever it is that you wanted to go to the library or just check on Google. Let's start. Here's what we're going to do today. I'm going to talk a little bit about the importance of knowing kid thinking when you want to impact what they learn, and the teachers need to know that. I'll then give you, as quickly as possible, but I want to make sure that we understand what we're looking at, some pieces of evidence from the last 2 years that we collected data. When teachers do know how kids think, how do they make a difference in their life? We'll talk about that with Gülseren's question. I will talk about 4 main elements of conceptual progression in numerical knowledge. What comes before concept of number, then what some of the milestones in reasoning with the concept of number, whole number, then multiplicative reasoning with whole numbers, and fractional reasoning milestones. So I'll try to show all these 4 You probably asked yourself, where's place value based in? I'll point out, it's not where it is taught in most of the world. And it is taught way too early when kids are not ready and they don't get it. And then later on, you try to help them catch up, as opposed to just establish the foundation they can have it. I'll point it out. We'll have a short discussion and we will have questions and answers. I want to talk about the question. Any time you want to ask a question, please do. I'd rather answer questions as we go than at the end when you might have forgotten or it may got out of context. So just feel free to ask at any time. Let's go. So we talked about it last Tuesday. If we are carpenters, let's take another example. If we're bakers, we need to have some knowledge about how wheat becomes flour, and flour with some other stuff may become bread or a cake or baklava. That's the one I want to know. So in education, you have to have, and you need as a baker, you need to have some things to stir. You may need to have some places to get your flour, and you may have to have an oven. So they're tools of the trade of bakery. In teaching mathematics, we need to have tools of our trade. And beside the fact we need to understand learning, which is what we talked about last Tuesday, we need to also have some ideas about what, if we try to help learners learn, what is it that they are learning? What does it mean to learn? And the progressions we're going to talk about go there. But before that, the first thing about the tool of the trade and the importance is that to understand how kids think fit only with one of four perspectives. Our research over the last few years, and Tzur is doing some work on that too now, is only the last one. So these are standing for traditional perspective. You come to your class, you give a lecture, you give them some exercise, they go to home, do more homework, come back, and it's like again and again and again. Boring as boring could be. Most kids don't get the mathematics. Those who get it actually didn't need the teaching. Perception-based perspective is what we found, Marty Simon and I and other people as we worked through the years, when you start reforming teaching and you say, okay, lecture is not working, then what? We are moving into something we talked about Tuesday, and I'm not going to go into details. Then there comes something that we found in China, progressive incorporation. All of those ways of thinking about learning and teaching and knowing do not require understanding how kids think. A conception-based perspective, an idea that in order for me to help anyone learn anything, number one, I cannot give it to them. Number two, they have to construct it. Number three, they can only construct it by bringing what they do know and changing it. In order to do that, I need to know what does it mean to learn, what does it mean to know, and I need to have some kind of a map of milestones of that knowing, and that's basically what we're doing today. The other thing that is important, so you're hearing about the progressions. If you want to move to teaching that is somewhere here, you need it. You can't do without it. In the other three, you can. And that's where our research of kid thinking may not trickle into the curriculum. It can guide the design, and I'll share with you some of the results based on design of instruments for measuring where the kids are. So if you know that there is some progression, you can start measuring not just regular problem-solving tests and whatever, but specific to the content. What is it you want to know that they learn? Sorry. And as Tzur said and asked at the end of last Tuesday's presentation and seminar, so what? So what if we know how the teachers develop and they may move along and they may start traditional? Here's the so what. I'm going to give you some evidence to convince you that if the teachers understand how kids think mathematically and can use it to design lesson after lesson after lesson, and it takes time and effort and pain to get them there. Trust me on that. It takes time. 2-3 years for a teacher just to get to think that way. It is really tough. That's not easy. But once you get there, what I'm going to try to give you as evidence, so I'm trying to entice your brains to kind of, oh, okay, he has something to tell me that might help me too. That's what I'm going to try to do with the evidence. That when you move to that way of thinking and you start using the tool of trade of those progressions, your kids are better off learning. That was my answer. The higher you go on this and you make use of those tools, your students are better. That's basically what I'm going to try to do. Before we start, I want to help you get 2 disturbing realizations that are related to numerical reasoning taught in elementary and carried through people's life. I want to disturb you. I want to shake your thinking. I think that this will be true for all of you, or at least it was at some point, because all of us, including myself, grew up in systems that teach the following. Multiplication is repeated addition. No, it is not. Have you heard multiplication is repeated addition in your schooling? It's not. It's the wrong way of thinking mathematically. It is the way we teach our kids, and then we lose them, and we are so surprised why. Because we teach them it is, and it is not. Everybody is ready? Take a deep breath, because we're going to move to the next one. So also subtraction is repeated, division is repeated subtraction. No, it's not. Everybody is calm? Are we ready? Then you were taught that fractions are part of a whole. No, they're not. Sorry to tell you, they're not. Mathematically, they're not. And to learn mathematics, they're actually hampering anyone's learning. Repeated addition stops kids about 3rd or 4th grade. 50% of them fall through the cracks because they cannot follow place value, base 10, if they think of repeated addition. It's just impossible. They may do procedures, they may follow some rules, they cannot think. And fractions, well, I usually, when I talk with teachers and professionals, I'm trying to say jokingly, as the people in the United States say, oh, be my guest, try it. Well, everybody tried it in the last 10,000 years. It doesn't work. Why don't we start thinking about it? The progressions are going to address these two. So what does multiplication mean? What does division mean? What fractions mean? But they're not these two. And if I needed to stop here because of some time issue, I probably have done my stuff for you. But I asked it, well, then tell us more. Let's see some evidence. When teachers know what I just said, learn how to work with the kids, here's what you could expect to see. Oh, these are the, you can have access to the presentation later on. All the list of things. These are just to say, last summer we presented one. We now have 2 papers that were accepted for PME and PME&A. So I'm basically sharing things from the last year out of the oven of research. There are way more that I'll cite, and there is a whole page of references for people who would like to know. So you don't need to look at that more. Okay, let's start with this one. What we found is that the concept of number, I'll say more about what it means. So for now, it might be a black box, a placeholder. The 3 ways that we can say we have an indicator the child has a concept of number. One, let's take 8 plus 7. You ask them to do 8 plus 7, they say 15. You say, how did you get it? Child number 1, 8, 9, 10, 11, 15. Okay, that's called counting on. You start with the first number and count all the way up until you're done, because you have 7. Doubling, 7 plus 7, 14, plus 1, 15. Or 8 plus 8, 16, minus 1. Okay, everybody's with me? Break apart, make it 10. I'll take 2 from the 7, give it to the 8. That will make it 10. I still have 5 from the 7. 10 and 5 is 15. Following? Then you test them on multiplicative reasoning problems. things that would show what we would call, what most people in the world would call multiplication, not repeated addition. Bear with me. Those who had counting on, 17% of them could barely do that. Doubling is somewhere in between, 56%. It's not that if you have break apart, you necessarily will have multiplicative reasoning. But you can see that the strength, we call it strength of number, predicts your ability to reason multiplicatively. Now let's make it some reality. If you have 50% of your third graders engaging in multiplicative reasoning, they are here or below, you're teaching them something that is not going to work for them. They have no clue what you're talking about. That's basically what we found. Those who did have a stronger concept of numbers, some of them can. So you start seeing how the results, just go work with them, ask them, they'll tell you. These kids had no clue how to solve a problem. Let me give you a sense of what the problem in multiplicative reasoning. I gave Gulseren 6 towers. She put 3 cubes in each. How many cubes did she use for the towers? The answer should be 18, correct? These, out of those 70, the other 83% could not solve this problem, although they have a concept of number. It's worth knowing. Go ahead.
I'm sorry, 2 questions. One is these are hierarchical?
Yes, yes.
Okay, to make sure. And the second is how do you know that, how do you make sure that those kids doing the counting on and doubling or, the other one, they weren't able to do the upper, level of reasoning? Say the doubling.
Oh, we asked them, we interviewed them. This was interviewing. We found out that if we asked the kids to tell us how they solved and write it down, 50% of the time they tell us something else than what they did. So we actually figured out that there is no reliability on what the child says. So we interviewed all of them, asked them how they solve, asked if they have a different way of solving and so on. All of this, by the way, is in the paper, so you can go back to the paper and find it. But thank you for the questions. The other thing that we saw, so they had 4 problems in multiplicative reasoning to solve. Those who were counting on, which is weak, this is developmentally, that's a continuum. If you solve only 0, you don't solve any, or you solve at least 1, we did some analysis, rash analysis, and it shows that they don't have that way of thinking. They may have solved, so here's what they do. Those who could be successful, the 6 times 3, 1, 2, 3, 4, 5, 6, they drew all of them and counted once. That's not multiplicative reasoning. It's not even repeated addition. Just counting once. So they don't have that scheme that we call multiplicative reasoning, the first one. The doubling are still here, though there are some who are here. 2 or more means that you do have the scheme. These kids make a lot of calculation mistakes, so you have to really be careful of what you can tell. So if you don't have break apart, make it 10, which is a way of thinking not about the strategy, not that you were taught and you follow some routine, but that you actually can think on your own. You have no access to multiplicative reasoning, which is not repeated addition. We'll get why. Go ahead.
Yeah, I was just going to, they might have some ideas about counting on and doubling or the other one, but can you give some examples for the problems, multiplicative reasoning problems?
I did. With the 6 towers, 3 cubes in each. How many cubes in all?
So which level, which question was that?
That was number 3. So this would be that one. We are now having a paper that would publish actually the whole instrument. That I think it will come in a PME in Sweden. Here's another one. So we measured. Now that we worked with teachers for a whole year. We measured before the beginning of the year and at the end of the year and compared 2 things. So this is comparing the same student, the same school, the same teachers, before we started, end of year, after 1 year of implementation, when they learn progressions, how to think where the kids are, and so on. We have 2 schools and all our project together. What is school B here later will become school. I don't know if you're familiar with effect size. That's very high. In education, 0.25 is a good thing to have. that over 1 year or whatever period of teaching, you would have 0.25 effect size. It's a statistical measure for that. So this one did not grow much, but hold it. This one grew a lot. For those who've been on Tuesday or are interested in what's the difference, most teachers here start as a traditional. Most teachers here, we started with them, they were already at the perception-based perspective, so they were higher on the level, so there's just way more move here than here. And this is basically the total. So you can see that at the end of 1 year, the students are doing better, these are the 3rd grade, on multiplicative reasoning. No, substantially better. We also did, within the year, for the same students, fall and spring. So we measured where the kids are at the beginning of the year and where they are. So we're not talking about the same students, comparing apples and apples. You see how even in school A they grew. So they grew compared to what was there before, so it actually works. And within the year, you can say, well, why is this important? How do we? Because they actually are better at the end of the year than their counterpart a year before. So you can tell, again, this is a huge effect size. You took kids who did not have multiplicative reasoning, and at the end of the year, you really brought most of them to do that.
How many kids and teachers?
Say it again.
How many kids are these students?
I think the N here is in the neighborhood of, yeah, I think it's at 500. Yeah, we're talking about large N. Within school A, we had some teachers that participated and some that did not. Again, spring 16, spring 17, basically comparing between 2 years. So you're saying before they started, at the end of the year, what they got, at the end of the year, after they got it. You probably could guess that these are the non-participating. This is that little impact. That's why I said wait. Because although there was not a lot of impact for those students, they grew up and the others went down. Let me translate this statistical stuff to reality. Teachers worked for a whole year. We paid them a lot of taxpayers' money. And at the end of the year, the students were worse on multiplicative reasoning. If you start thinking, maybe that's because of repeated addition, I would not blame you. It is. If you teach repeated addition, the likelihood of solving those problems that we gave them that require reasoning, not just adding some numbers, was not working. Now comparing fall, so the students of these teachers, so this is comparing before and after the same kind of time in a year. This is the same group of students, so they did not change much. And see how the others grew. So our teachers started with a group that was much lower than the treatment and grew way above it. Everybody's reading the graphs perfectly. You're all in math, so I know that I can trust that one. Let's have some more. Now we're moving, so this was about the first scheme. Now we're talking about 2 other things in multiplicative reasoning. One, the earlier is called same unit coordination. We get there. The other one is mixed unit, which is the one anyone needs to know place value based on number system. Mixed unit coordination. If you don't have it, you don't have place value. You can teach it as much as you want. The kids get nothing. No meaning. We did the same in China, and I'll say something about it. But this is from the United States. On the left side, you see no same unit. On the right, you see, yes, and now these are 4th and 5th graders. So just to get a sense of what the population is, again, like in the neighborhood of 400, 500 kids. Actually, here we have maybe more. I think the other one was in the neighborhood of 200, and these are the neighborhood of 500, because we're talking 4th and 5th, and they're broken into those groups. So 61% of 4th graders did not have that thing that we call same unit coordination. 40% had it. In 5th grade, that's serious. Let me tell you what same unit coordination would look like. I ask you, Zelha had 9 towers, 3 cubes in each. Golsaran has 4 towers, 3 cubes in each. Who has more towers? Zelha. How many more towers does she have? 5. Everybody's with me? 9 and 4? How many towers do they have together? 13. 9 plus 4. Everybody's with? That's what same unit coordination is. You're operating on those towers, not on the cubes. And you answer it. 50% of 5th graders could not answer those questions. It's the same in China. The numbers are higher, but it will be like what we got with our teachers. But there is a problem. It's not trivial. And then what we said, well, look how, if you do not have the same unit, 30% of you might do mixed unit and place value. If you have it, you don't, then you basically have no chance at mixed unit and place value. 5th graders, 4th graders. If you have it, you have a better chance. And the same thing, if you don't have it, not really. 41% have a chance at it. So we now see how this progression of units and coordination, all the stuff, will bring it up, allow you to predict what these kids are. The last one is nice because we can show what happened when the teachers started using this same unit, mixed unit. What are you talking about? This sounds like Chinese. I was in China, I can tell you. 4th graders. Here we have all the statistics. 30% of those who could not do it in the fall, 60% of those students could. So think about it. You double the number of your students who could do place value based 10 at the end of 4th grade. This is a nice thing to report. 5th graders started higher, of course, and grew up more. When you know how the kids think, you have better chances in allowing them learn what you need. I think the last one is the one that probably is important for everybody because we work in systems that test them nationwide, statewide, whatever. So this is from the results before and after grade 3 and 4 in what they call PARC. Now they have in the United States 4 levels that they measure. One is if the kids are proficient, basically they know what we want them to know at the level of the grade, or they are advanced, they're even a little above. So we combine those two and we say in Colorado, 2016 and 2017, 3rd. 4th. You see that it was the, let me see. Yeah, 3rd moved pretty much nothing. 4th moved pretty much nothing on the overall test. This is in the district where the school resides. 3rd moved a little bit. It's not statistically significant. A little bit. It's not statistically significant. The school C, it's the school B that you saw earlier, just that we are using different, this is from different papers. They had 0% of proficient and advanced students. At the end of the year, they're about, see where it is. The same for 4th. Growth, not as much because it takes more time. What 4th are tested for is not necessarily reflected in what they got in the teaching. Are you convinced that there is a reason to learn about these things? Let's talk about them. How much time do we have? When do I have to finish?
Maybe 25 minutes.
25 minutes, cool. So what I'll do is I'll just go quickly through those. Each of them is published. There will be papers you can go to see and so on. Just give you a sense of what we're talking about. So at the end, you can tell, okay, I want to learn more. If I could come here and after an hour of working with you, because of the data you just saw, you would say, oh, I want to know more about same unit. I want to know about a unit fraction. That's where we're heading. So this is based on a lot of work with Les Steffi. First thing that we are not talking about kids who have concept of number. We're talking of those that need to prepare for it. We have a lot of those in our 5th and 7th grade and 9th grade. It is painful to see, but it's true. So I don't know in Turkey. I just know in the United States. Rote counting, I can say 1, 2, 3, 4, 5, 6. I can sing the song. I can just say the words. When I have that, I can start coordinate the words with my objects. 1, 2, 3, 4. I can order them. I do not skip words. I do not count like 1, 2, 3, 4, 5. I just one-on-one correspondence. And then there's another thing that most of the world is not looking at, but is really important, comparing. Zela has 14 cubes. She just put them out. She gave me 11. Who has more? Zela. How many more? We'll talk about that. But can you tell me, how do you know that there are more? I put the 14 and the 11 near one another, and I'll round them in pairs. That's one-to-one correspondence. And at the end, there will be one person. Either we both ran out of those cubes, or one of them still has some. That's one-on-one that is not taught in the world, and it's a serious issue. Then we come to what is called subitizing or subitizing. Comes from a German word, so you can probably say it either way. Subitizing is that ability. Everybody watch me now. When you think that you know what the word for that in Turkish, for that number is, say it, okay? I want to hear. The first person, I usually in my classes for the teachers say, the first person get a star on them. All right, ready? In Turkish, don't say it in English, Turkish. Gulseren got it. Let's do it again. I don't hear you. You apparently don't have subit. No, I'm just joking. All right, so some people call it manliness. It's the ability of the brain and the mind to recognize small quantities without having to count again everything that was there. So once in history, I counted 1, 2, 3, and I saw it, and 1, 2, 3, and 1, 2, 3, whatever. And I can tell it is going to be 3. I don't need to count anymore. It's leading to number. It's not yet number. Then we have what Les Steffi called perceptual or concrete counters. They can tell how many there are. You have, if you put a few items and you say, how many chairs? 1, 2, 3, 4, 5, 6. Now let's move this one here and move this one here. How many chairs now? If a child says 1, 2, 3, they don't have it. If the child says 6, and look at like, why are you asking? I just did that. Then you say, okay, the child has manyness. They know that at the end of counting, you don't need to count again. Unless you added something or you took something out, you don't have it. That's manyness. It is not yet the concept of number, which we talked earlier, that leads to knowing or not knowing multiplication. Piaget confused us all because he called this conservation of number. When the child does not need to recount, Piaget called it conservation of number. We call it conservation of manyness or numerosity. It's not yet concept of number in this level. Some people say it is, and it's a choice. I'll explain why we do that. More and fewer. So Giselle has 14, Ron 11. How many more does she have? Here's a child who would answer the following. Giselle has 14, Ron 11. Giselle has more. How many more? 14? Makes sense? She has more and she has 14. How many more does she have? 14. What are you asking me about? That's a fallacy that kids bring to you. And if you blame them and tell them, no, it's not, you probably are not going to, you have to work on it. So they have to learn through one-on-one correspondence that more or fewer refer only to the thing that is left when somebody ran out and the other one still has some. That's something to be learned. That's not easy, but be ready for that. We've seen so many kids doing that you probably would have some on your side of the ocean too. Both sides of the Bosphorus, I would assume. Then we have figurative counters. So we no longer need to count the chairs. If I covered all these chairs after I established there are 6. Let's do it with the cubes. She has, we said 8. 8. Now it's 8. And I have 7. And she took them off. You cannot see them. So you're saying, Zelho. That's figurative because you count those. You don't count the cubes. You put some item for it. Some kids do this or that. Whatever it is, they create an item for something that they needed to count because you covered or whatever. They can start counting units that are not tangible. They cannot see them. They cannot touch them. They have to actually produce them. That's a crucial step toward moving from concrete to abstract. It's in between. First, it is still concrete, but it is produced for something else, so the brain can start connecting those units and no longer depend on the actual thing. We see a lot of kids who still have to count based on what they have, and they are not here even. And the last one, which is not yet number, counting all. How many does she have? 8. How many Ron has? 7. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15. Okay? That is not yet a concept of number in this theory. Some people say it is. We choose not to, because when you have counting all, you're still operating on units of 1. You count once. You don't count 8. If you do 8, 9, 10, 11, 12, 15. You started with 8, so you took 8 as a thing. It's not just all these ones. It's like a thing in and of itself. It's a unit. And then you need to stop at 7, so 7 is also, and you start. So that's why we said counting on is a concept of number. Counting all is not. Some people want to do that, and what they do is they lose the students who they think have concept of number whenever they start teaching things that require you to have that concept. They need to go back and count by ones. Have you seen some of those students? Maybe your children, maybe your nieces or nephews, maybe your... I've seen so many of them. Every time something comes up, let me give you an example that maybe you recognize yourself. If today is Thursday, what will be the day of the week 10 days down the road? Sunday. How did you see what I'm saying? We still, in some cases, rely on counting ones. We have to do that. I do it all the time. I can't, no, it's not, I'm joking, because I can use the base 7 in the system to understand why would I say, because 10 is 7 plus 3, and I can do the Thursday next week and then 3 more. That's how I did it. I did not count. But many people do. Many adults do. They did not yet develop number as a thing. They can think with 7s. And just so if today is Thursday, what would be the day of the week in 49 days down the road? 7. It would be Thursday. That's 7 weeks. That's it. The same day. That kind of thinking is not available to people who do counting on. They will basically go, oh, Thursday. Yeah. In the meantime, the other kids moved away from the test to the next topic in the school. So these were pre-numerical. They are all crucial. You can't have the concept of number unless you had all of those. However, now we move into having a concept of number. So we're going to slow down a little bit. All of those are available on the PPT for you, PowerPoint, PPT, or in books, in articles.
I actually wrote in Turkish too.
It's available in Turkish. You can translate it for me. Counting on is the first indication that a child has a concept of number. Concept of number means that at least some of the units they take for granted and don't have to reoperate on the ones. It might be a 2. It might be a 3. Definitely when somebody did 8, 15, the 8 was taken for granted as 8 ones, and I don't need to recount all the ones. That's why we say it. In research, I'm not going to go in details. Research that Matt Lambert, a master's student of mine, and I published at Jeremy. Yeah, master's student can get a research that will be published at the Journal of Research for Math Education. We suggested there are actually 2 parts to counting on, which is based on some of the work that Karen Fusen did. First, you need to know where to start. 8. Some kids start at 10. You need to know to start at 9. After 8 comes 9. The other one is you need to know to stop, and some kids don't know to stop. They start at 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Oops, I forgot to keep track and know where to stop. So these 2 are really important. That's concept of number. I'll stop here for a second. Concept of number does not mean you can count. It does not mean you can add, because counting all you can add. It means that you take a unit that comprises of some ones as a thing for granted. You don't need to reestablish every time you use it. Questions or comments about that one? There's nothing more foundational than this one. To say, if my kids cannot do it, what do I do first? Do they have a concept of number? Questions? Now that they have it, they can also go to I'm not bringing in doubling, but missing, adding, and counting up to can be indications, stronger indications that the child has a concept of number. Missing, adding, Zella had 8. Ron gave her a few more. Now she has 15. How many did Ron give her? Missing, adding. That's the problem. Now I'm counting up to 7. He gave her 7 because I went from 8. It's not counting on because the goal totally changed. And the goal in the first one was find the total. The goal here, I have the total. I have one of the parts. I need to find the other parts. That's a whole different thing. And I can do that to do subtraction. That's a stronger sense of concept of number. I took for granted 8. I took for granted I would stop at 15 because I know what it is, and I found out how many ones would make it. Then comes break apart, make a 10. Dutch people call it through 10. Take 8 plus 5. 2 given to the 8, that's 10. I still remember the 3. That's another example. Break apart, make 10. Many teachers in the United States teach this as place value based on number system. It's not. It's just an ability to decompose the number 10 into 8 and 2. Then to decompose the 5 into 2 and 3 and give that 2 to the 8 to make a 10. So it's a strong sense of number because you can take it apart without losing what it is. But that's what it is. It's not base 10 at all. It has nothing to do with it. Base 10 system has to do with powers of 10 from the right to the left. How is this related? Zero relationship. You can do it with words. It has nothing to do with the 1 and all of this. I did that. One of the things that people say is that constructivists are against, and constructivist means all constructivists, are against facts and procedures and so on. At least you see one here. I'll talk only for myself. I know there are a lot of others who don't say that. It's just about when do you teach it and how do you teach it. So here come the fact family. 8, well, let's do 6 plus 3 is 9, 3 plus 6 is 9, 6 plus 3 is 9, 9 minus 3 is 6, 9 minus 6 is 3. Do kids need to know that? Yeah. Because they need to know how to decompose units to have a family. This, what I just demonstrated, is that 9 is a composite unit that I can decompose into 3 and 6. I assume each of you can decompose it into 2 other numbers that are not 3 and 6. And then we can get to 10. 10 is made of 6 and 4, 5 and 5, 7 and 3, 8 and... We need the kids to have that, but what we are assuming is that they need to decompose the larger unit into 2 parts. If they don't have it, well, why are we teaching it? Procedure, maybe they'll remember, maybe not, but that's the best. But I think that we need to have that. Last comment about numerical milestones so we can get to multiplicative and fractions with some time. There's a hugely important program in the United States called Cognitively Guided Instruction, CGI. They did an amazing piece of work over the years in 2 ways: identifying problem types or task types and helping teachers learn those and use them to teach. They have 11 problem types. They say the point I'm trying to make, and then I'll go further, and that's my interpretation, and that's my bias. I disagree with them. So I'll say it as honest as I can. They have problem types, and they say whenever the child can solve independently and robustly each of those types, that's their conception. That's what they know. That's a way of thinking. Nope. I disagree. Example. And by the way, the example I am taking is from their writing. They just dismiss the meaning of the example from my perspective. I don't. Here's a child who's giving, let's say, join problem. Zell had those 8, and Ron gave her 7 more. How many does she now have? We joined 8 and 7, right? Child 1. Child 2. Child 3. With 7. Child 4. 8 plus 7 is 15. How do you know? Well, I'll explain to you what... no, just tell me how you get it. I don't get it. I thought it's 17. But they have fact retrieval. All 4 could solve the same type of problem. If you agree with me that counting ones and counting composite unit is different, then it's not the same conception. I take the example from them, not from me. I can bring a lot more. So I disagree that the way the person thinks and the way an adult looks at a problem are synonyms. That's where we differ with the CGI. Other than that, what they did is amazing, and how they supported kids' learning is, I still am waiting for myself to learn how to do what they did. I am just starting the work with teachers. What we're trying to do is teach a teacher's conception. That's something they did not do, so we have to learn to do that. Multiplicative reasoning. Any question about numerical reasoning before we move on? I'll summarize it for you with one sentence. If the child does not have the concept of number as composite unit, the child has no future in mathematics. So I translate it now to what I do in schools with our teachers. If the child graduates 2nd grade, moves into 3rd without a concept of number, we are responsible for their failure in math. That's it. It's simple. And the teachers take it seriously. The teachers we work with, oh, I have to do this. Now, we worked with 3rd, 4th, and 5th in this project. In the previous project I worked, they now see it. All these kids coming in their classes and have no concept of number. Or have only counting on when they have to teach at 5th grade fractions. It doesn't work. So that's the summary of the whole thing. Please.
I have grown up with reading about CGI stuff, and now that you brought a different perspective on, as I understand your work, you start with the kids, you give them tasks to do, you observe them carefully, and the epistemological piece is how they think. You try to inductively come up with ways to describe how they think.
Right.
Right?
Yes.
And that's, you develop a theory. Now you attach value to those. This is more advanced than that, this is more elementary.
Absolutely.
How was CGI's methodology similar or different than yours?
I want to do 2 things as a response to your question. One is make sure that we have a time, but maybe not now, to address it in a more full sense. But in a short sense, the answer would be, what is the epistemological stance, philosophical stance, of what constitutes number, addition, subtraction, and so on. For constructivists, what constitutes it is the mental operations on units that we have to make inferences, we have to interpret it. It's not available. I need to say what is the child doing and find out from this what they actually, I think they have. They said this, whatever is not, it's basically a behavioral stance. A behavioral sense. If you don't have, if you cannot see it, you don't know what it is. You cannot make inferences, you just see what the kids give you. And so if you can only do the stance on the tasks, and what you collect as data stops at what was the behavior and the performance. And we're saying it's a different thing. More than that, what is the methodology and what we're looking for and what we analyze and so on is all relying on that difference in an epistemological sense. I would say that as a short answer because I think that's important to address. But to go into the methodology, you would have to have a much deeper discussion about these differences that are very important. And they basically had an argument. So Tom Carpenter, Elizabeth Fenema with Les back in the 70s and the 80s about why are you not measuring it? This is, you're giving the kids, who knows what happens in their brain. This is a very important argument to have. And some people say, I don't want to deal with it. The most important thing for our discussion here, and this is why your question is so at the heart of everything. There's a lot. Paul Cobb once told me when we had a conversation about that, he said, I tried and tried and tried to give and work with teachers so they can develop an understanding how to make an inference about the child thinking. And he said, CGI solved the problem because you don't have to engage the teacher. It's something the teachers cannot do. I said to Paul, I don't believe in it. And went out and had a project from the National Science Foundation to try to prove it. What you saw, the results, are results of me telling Paul that's not true. Teachers are very smart people. It requires a lot of attention and patience and work and hard and tears and whatever. But that's not true. That's why your question is so important. If you assume teachers can only learn CGI, they cannot understand kid thinking. Truly understanding how the kid thinks is the result operating differently as a teacher. Then let it go. It is not worth of the time. That's my answer.
Yeah, it makes so much sense. If you try to understand something, look into it. Child's thinking. Start from where they are, and then try to reach to generalizations and attach meaning to them, and that makes a lot of sense.
But the difference, if I can add, and what he's saying is CGI, they look at the result. If the child can add 8 plus 7 and give you a result, it can be, they don't look at how the child is getting the result.
And what could possibly underlie doing this? Because we're not just looking at what the child was doing, but actually, what could possibly allow the child doing this and the other child could not, or the other way around?
Yeah, problem types, it is kind of very useful for teachers to use. You can label that as a missing element, for example, but not necessarily how the child is solving it and what it may mean for her development, for example, multiplicative reasoning or fractions.
Like the example you gave, would be 4 or 5 different ways you could reach the same result.
Yes.
So you have not heard yet place value, and let's go quickly through multiplication, multiplicative reasoning, so you see. The prerequisite is break apart, make a 10. You just saw it at the beginning. If you take someone with a concept of number that is weak counting on, you're likely not to get them to multiplicative reasoning. So everything here is based now, this is new. 2 years ago, I would tell you if they have counting on, move on. I'm telling you now, hey, we learned it, at least if you want to use it. So we start with a scheme we call multiplicative double counting. These are 3 towers, 2 cubes in each. The question is how many cubes, and what they do is they coordinate how many towers with how many cubes. They start, say, 2. I hope that you don't need to go to the optometrist and check that this is not 2, this is actually 1. If you need to go to the optometrist, I can loan you my glasses. That's a joke. 2 is not 2, it's here 2. I have a composite unit, one of them is 2. The second one is 4, the third, I counted 1, 2, 3, not 6. That's what double counting is. I count at the same time the ones in each unit and the number of units that hold them, and tell you at the end how many ones there are. It is not repeated addition because of the following. In repeated addition, say you have 2 apples, 2 apples, 2 apples, and you say I have repeated these 3 times, I have 2 plus 2 apples plus 2 apples plus 2 apples equals 6 apples. Did you hear any unit changing? It did not, because I said apples all along. Let's do it this way. I have 2 apples in each basket. Apples per basket is a unit. 2. I have 3 baskets. That's a different unit. And I have 6 apples, which is the third unit that changed based on these 2. That's where repeated addition doesn't work, because in multiplicative reasoning, which is everything past, go geometry, go stat, go probability, go algebra, whatever, slope, wherever you want to go, repeated addition doesn't work. It has no meaning in multiplicative reasoning. You are maintaining the unit. Move on. Same unit coordination, the one I told you. You have 3 towers of 2 and 7 towers of 2. Who has more and how many? You have 4 towers more. How many do you have together? And so on and so forth. Now, just for the sake of communicating what happens in the world, this sounds to any adult, teachers included, as the most trivial thing. Try it with your kids. We tried it in China. 40% of the 4th graders and 5th graders could not do it. I was like, whoa. That was an eye-opener for me. And we basically, with the work we did with our teachers, got the kids to be where the Chinese are. Now, if this is a prerequisite for what's come up, we better spend some time on it. It sounds so trivial. It's one of the least trivial things that you've ever seen working with kids. Then we have unit differentiation. I don't want to go into a lot of details. The most important thing, this one, and a paper we have at PME in 2009 Thessaloniki, is the basis for the distributive property of multiplication over addition that our teachers teach to the kids. Say it, put it on the board, give 3 examples, and give 20,000 more for the kids to solve. But if you don't have that, I'm not going to go into details. You don't have access to the most foundational property in arithmetic. And you don't. Basically, most teachers teach this as repeated addition, and they jump to division. And they lose their kids for the most important property in arithmetic. And that's where you get place value. You go to mixed unit coordination. Think about the following. You have 7 towers of 5 cubes. You have 10 more cubes. How many towers would you have if you made these into towers of 5? Gee, if I said about this one being a leap, try that one. It's huge. Nobody in the world does. Well, that's not true because our teachers do. And this one is the basis for place value. Not this, even not repeated addition, but real multiplication. Not this, not this. These 3 together combine into that. Now, this is probably taught 3rd. This is taught 1st grade. Ron, how do you explain? I don't. It's beyond me. I'm honest. Developmentally, our kids are not ready for place value until they have this, which probably will develop at 4th or 5th grade. If we help them develop it. And if not, they are lost. Quantitative division, partitive is pretty much what is in the literature, and we can move to fractions quickly. Oh, yeah, and then do it with facts. 6 times 7, 42. In the middle of the night, you wake me up, I know it. But now I know it based on all of this, and I need it. Last but not least, fractions. I'll just go show you that there is a whole picture, because we don't have time, and all of those are in the literature. These are ways of reasoning that are based on unit fraction, 1 over n, m over n, and so on and so forth. And these are, okay, take 1/9. Take half of it. How much of the whole is it? This is what we're doing here. I'm not going to go through, these are available in the papers that are in the references. I just want to suggest that each one of them is huge because of the following. 1/5 is a fraction that depends nothing about being part of a whole that has 5 equal parts, which is how all of you, everybody in the world have been taught and probably is still teaching. Part of a whole. Fractions are not. They're multiplicative relation. We talked a little bit about it on Tuesday. 1/5. Let me give an example. What's your name? Mehmet. Mehmet has went to the market and bought 3 apples. Zela is such a nice lady. She knows me for a long time. She said, Ron, here are your 15 apples. Would you agree that Mehmet's apples really in relation to mine are 1/5? Are his part of mine? No. He want to eat them. He's not going to give them to me. And I can take my 15 and spread them around the world. I can do whatever. They would still be 1/5. It has nothing to do with part and a whole. Now let's say that I want to see what 15 is as a fraction of 3. 15/3. It is a fraction. It's larger than the whole, several times. How is it a fraction? For children, for adults, it's not. Part of a whole doesn't work. The rest, we don't have time, because I want to give you time. I'm going to skip those. Leave them here if you want to look some of those and question and answers. I want to close this so we have time for questions and answers. But these are the main points I wanted to say. I want to close it so we have time for questions and answers. Well, Zelha asked all her questions. She cannot ask more.
No, I'm just thinking maybe we should get the microphone if someone is so people who are watching us, they can
If there will be no questions, I'll give you answers. But
I was wondering if you've seen exceptions to the trajectories. Because it seems so contextual or cultural, like you have work in China and you work at schools with different cultures. And
so these are crucial questions. We just, the trajectories have been produced, some of them in the last 5-10 years. But we started in fractions and in multiplicative reasoning to do some work in China. The same. We did work with teachers. This is one of the points here. If the teachers don't have those, how can they teach it? So we see the same with the teachers. Now, they're not straightforward in the fact that there are not gray areas. Someone would go and come back and so on. So these are things to be explained. So there were a few of the kids who had counting on who could do double counting. There were a few. Overall, when we do education and we teach a class of 35 kids, that's what you do. So there will be 2 outliers in my class, but I rather know where all the others are with some better certainty of where they are and cater to it. We see it in China. I'm trying to think if there was any other cultural context that we could compare. You want to do? We took the whole thing, translated it in Chinese, and we did a whole work, and we did interviews with the kids, just like they did in. Everything was translated. I'm talking back and forth. I actually could use the most important thing from my perspective. I could use those trajectories to make sense of Chinese kids when I understand probably 20 words of what they say. Literally nothing. They would solve problems, and I can say, okay, did you think about your problem when you gave me this answer? They just gave the answer in Chinese. No translation. I'm asking them not to. Did I get it? How can I do that? That goes back to your question. I can infer how their mind worked because I have that trajectory, and apparently it fits. We worked with 4th graders. In China, there is no special education separation. All the kids are in one class, not 35, which you think probably is really crowded, definitely compared to the United States, 45, 50. You go into that class, and the teachers know where they are. And they gave us 5 kids. We worked with 4. The other one, it was not really helped. But so you think about 10 to 12% kids that in the Western world would be called special education, learning disabled, and so on. And we worked with them, and they were just working with us. If they did not have a concept of number, no double counting. If they have double counting, we can go the same, just the same. Do I say this is universal? I would suggest, okay, so your question is really important. This research was basically originating in Western cultures. It was now tried, at least in China, which is a very different culture. Hey, now I'm really saying, be my guest, take it and go to kids in Turkey and see what happens.
Actually, last year we did interviews. We had 17 interviews, 2nd graders, and we can talk about those. You remember the questions from last year? But they were really good kids, so probably, the students that they interviewed, so probably we didn't see much.
I would bet you that if you took them to something higher on the fraction level, they would not have it because they learned it as part of a whole and they would not be able to solve it.
They did 2 interviews, 2nd graders about numbers, 5th graders about fractions. Yes, fraction was a lot different.
I'm not surprised because at some point you can no longer just go with the system. You have to develop that thinking. You have to do it for yourself because otherwise nobody's doing it for you. Up to a point, multiplication, division, you can carry some of the procedures, do whatever. It's where, I would say we lose probably 50% of our students about when we go into multiplicative reasoning. And out of the 50 that are left, probably another 30%, so we have about 20 left by in 5th grade that are still learning mathematics. Everyone else is not. And it's kind of conjecture, but we have to study it and get empirical. But that's where we are. I would not be surprised to go anywhere in the world and work with people, no matter what their age, after they studied fractions, and give them a question, and they cannot address it at all. I did it in Singapore last summer. Teachers from around that country. Now, you know Singapore is number one. You know that? They could not solve a problem. Teachers! I'll give you the problem so you see. Think of this. 1/4, everybody's with me? Same stick. I don't have the picture here. 6 not equal pieces. And one of them is equal. What fraction is it of this one and of this one? They could not answer this question, which is 1/4. Or they could answer 1/4. They had no idea why. It's so easy to take anyone who learned fractions as part of a whole and throw at them any problem that they will not be able to solve. And it's like, why? Because it's not part of a whole. Go ahead. Mehmet, right? Go ahead.
Well, I think, more explanation or more examples about the situation there, because I think I need more explanation and more examples about the situation, because 1/5 of something can be explained to a student as we divided into 5 parts and we are taking one part. So this is 1/5 of 5. That's true. But what is the situation that you are not addressing that into the other side?
Hopefully. Here's an example.
Yeah.
Stick A, 4 equal parts. That will be, would say 1/4. This is 1/4. This is 1/4. It's 1 out of 4 equal parts. You might have a pizza, shading, blah, blah, blah. Everybody has seen these kind of things? We teach it all over the world. Stick B, same length and width, okay? I just copied this one. And I actually copied this to be the same thing. I added another line here and 2 here. Do we have 1, 2, 3, 4, 5, 6 parts that are not equal?
Yes, we have not equal.
Question for you, the shaded part. What fraction is it of A? With part of a whole, you cannot answer this question because it's not part of it. I hope you see it's not part of it. It is 1/4, but it's not part of it. So how do you answer it? That's a problem many students have. Now comes the one that is even more complex. It is a fraction of B, but it has 6 unequal parts. What is it, 1/6? What is it? If you say 1/4, which it is, part of a whole does not explain it. The only way to explain it, which we call multiplicative relation, and it comes in all of those. Let's look at because the width is the same, so the length of A is 4 times as much as this one. It's 1/4. Your 3 apples, my 15, is 5 times as much as it. Yours is 1/5 of mine. This one, the length, is 4 times as much as this one. 1/4. Everything that is the whole is so many times as much as the other one. That's what the fraction is. I need to teach very little thing about it. It takes a lot of time. It takes work. But once you get it, ask the teachers in our project what happens when their kids actually got that. They go through fractions like nothing stops them. If you need to think part of a whole, as soon as you have no parts, no whole, they're not equal or whatever, they don't know what to do with those. One of the typical questions that we see all over the world, PISA did it. More than 50% kids in the world. Now say this is 1/3, which makes sense for the child. It's 1 out of 3 parts. And the teacher said, but they forgot they have to be equal. They did not forget anything. What are you going to do with it? I know it has to be 1 of 4. But it's 1 of 3, and they told me not to draw the other line. What do I do with it? I try to apply something I do know to what they gave me. It's 1/4 because the whole is 4 times as this one, and I can explain why. That's the kind of examples that I hope enrich that discussion.
So we need more specific explanation about telling 1 of 4
Not explanation.
something
They
like
need
that.
to engage in activities that allow them to actually come to construct it, and that's not an easy thing. I did it in China. Kids had a lot of fun. I did it in the United States. I did it in Australia. I did it around the world. You invite me again and say, Ron, get to this class, work with us. And I'll do it with Turkish kids. I love doing it. It's so much fun working with the kids you cannot imagine. When it's work, and the most important work is with the teachers to take what you say seriously and say, I'll try it also. Once they do, which is really hard work when the teachers to accept that, kids go like that. It's amazing. It's amazing to see. Here's one thing that I want you to record from all of this. So I did a presentation, seemed not like this, all about fractions in a psychology department in China. At the end, 3 professors stayed with me 2 more hours arguing that fractions are part of a whole. And I was having so much fun. It was amazing. They could not accept that fractions are not part of a whole.
Is it something? Does it have some relation with the language also? Explaining.
I don't think so. The way we think about it goes back to the question of what are we paying attention? We're paying to the unit and the relation or operation. And so if I take this unit, 1, 2, 3, 4, I can tell you that the whole is 4 times as much of it one way or another. I can take the 3, 15, whatever I do to show that how many times the Americans have a term called goes into. They use it a lot in division. How many times 30 goes into 210, okay? How many times 3 goes into, so they say gozinta, okay? Gozinta, they talk Turkish. So how many times this one fits in the whole? Allows me to answer how many times the whole is as much of this one, which creates the relation. That's all I need to know about fractions. And
Thank you.
a 3/4 will be 3 of those. That's all I need to know. Does that help? I'm very happy you brought the question, because anyone who leaves this room would say, I still don't know what fractions are. It will take long work, but it is something that we can do with the kids, we can do with the teachers. It is hard work, but it's possible. Go ahead. There's another one? Oh, okay, go ahead. Oh.
I'm trying to get the deeper meaning. I'm sorry. I'm trying to understand the deeper meaning of fractions not being necessarily parts of a whole. And let me try something, see if it makes sense to you. From elementary school to middle school, we are advancing from additive reasoning to kind of multiplicative reasoning, and then rational numbers and fractions. If I have to place fractions f between 2 symbols, cross, addition, and multiplication, I tend to think that fractions is conceptually closer to multiplication than much more than it is to addition, because it is the backbone of proportional reasoning. Also, it is related to proportional reasoning.
Yeah.
Parts of a whole reminds me conceptually some kind of an additive kind of reasoning. I know my language is crude, but I'm trying to theorize here. So could it be that what you're trying to say is that fractions are relatives of, conceptual relative to multiplicative reasoning?
Oh, yeah. Yeah. Basically, what you're saying is exactly what we're trying to say. Everything about fractions starts with a multiplicative relation, a multiplicative operation. There's one caveat to it. Learning about unit fractions, 1/4, 1/3, 1/5, 100, does not require all those schemes of multiplication. As soon as you move to 3/4, let alone to 5/4, let alone to 20/4, you need to have multiplicative operations. Absolutely. So fractions are basically an explication and a specific application of multiplicative relations between 2 numbers, but not whole numbers. So we're operating on the one inside as opposed to on the one outside to have larger units. And that's one of the changes the kids need to appreciate. When I operate within one, each unit becomes smaller. So multiplication in fractions makes smaller because I'm using units that are within the one and not outside the one. So that's part of it. We just, in the references, you would see a long list. There's some piece of work that came out of Marty Simon's work recently, Goserin's advisor. A lot of work about fractions, multiplication of fractions, and so on. So you would have all of those. You don't need to copy them or anything. But more and more comes out that if you teach fractions, not as part of a whole, but as a multiplicative relation, and the kids deeply understand that, and the teachers, of course, need to, then they have a chance at understanding fractions, proportional reasoning, ratio, slope in linear functions, whatever it is, wherever you go with it, in a way that is not comparable to anything that is coming up with part of a whole. Part of a whole really gets them stuck. That's what it does.
Right. And it's I suspect that it is a product of our primitive theories of how children learn, and we impose our own adult ways of thinking, how we think children learn, and we say there are 4 different representations, 4 different models of fractions, and this is what it is, and this is how you ought to teach it. But that's our theory that we're imposing on it, not necessarily.
In all the languages and words and cultures in the world, there's one word that I would say now, you would recognize, although it might be in different, amen. Yep.
Okay.
Yeah.
All right.
We try to impose our adult knowledge on the kids. Quite often it is part of a whole or a repeated addition or whatever, but the kids think differently. And if we don't learn the whole talk today, you just summarized it. If we don't learn and help teachers learn to work with the kids where the kids are not where my mind is, then we can't help the kids. We help ourselves. We get money for salary. We get, I don't know what, status in China. Teachers are looked up like deputy of God or something. But we don't help the kids. To help the kids, we need to try to think like the kids. All of the stuff I developed this morning, was about, I developed it last night, actually. I started working on this at 4 o'clock in the morning, so I'm still standing, I'm not falling asleep, but what I was developing here and what I was trying to convey is exactly, if you let go of how you think and try to figure out how the child thinks, this can help you. That's basically a summary of what we were doing. And it works, so the evidence I gave up at the beginning was, it works. The teachers are happier. The kids are so much happier because they have tons of games and stuff and so on, and they feel really capable. I can do math again after for so many years, my teacher. And the tests, well, they show it. In all honesty, I don't care much about the tests. Those standardized tests, national tests, state tests, whatever. A lot of people do. I'm not surprised it works that way. Because when you understand the math, the most important thing that happens is this one. People talk a lot about transfer learning. Once the kids really understand, no problem would throw them off. What they do in tests, they give them problems that would not be exactly what was taught in class. Then I don't know what to do with it because nobody ever taught me in a class. They didn't give me any homework, whatever. No, our kids have no problem transfer whatsoever. Because they understand, when they understand. If they have, I would start asking questions about what they do. I don't know how we do about time. I think that we are, but I'm ready to answer 20 more questions. 200, okay, 200. So I'll go quickly through just to this one. We talked about it, and I want to highlight something. That goes with your question. If we stop believing that what we know can be given to kids and instead figure out where they are and work with it, I'll say it as at the personal place where I am. I work with these kids regularly. Most of my life I worked with kids who are considered learning disabled. And I put that quote unquote because they're not. And it's painful to see them. It's painful to see a 5th grader who still can't. And a 9th grader who still does that for multiplication. It's painful. And I work with all of them. I work with them regularly and I enjoy working with them and helping them. If you start working from where they are, they develop self-efficacy. They know that they can. They resume their desire to learn. All of them came into 1st grade or kindergarten wanting to learn math. They love math. After a year, 2, 3, they're gone. And it does the same for the teacher professional. Suddenly, I just know why I'm a professional and why I came into this place. Why did I come here? So it impacts people's lives. As professional or as students. Students, their profession is to learn. In a way that I've not seen. It's empowering people in schools. And I think that if there's anything I could give you as my message, give it a try because the kids deserve it. I think I'm done.
So thank you for coming. Maybe we can have a last picture
Ooh.
together and we can fotoğraf çekmek